Okay, hello everybody, welcome to class today. I was experimenting a little bit with the cameras because I got a new camera, but I couldn't get it running, so I had to go back and put the old one, but I guess when I put it, I didn't put it right, so it was like showing into the sky. It was weird. So welcome to 202 Online. And so today we're going to continue talking about recursion that we've been talking about last time. And so we're going deeper into the recursive, the recursiveness of this, basically. So, yeah, let's just jump right in. Oh, and by the way, I should warn you that, well, not just warn you, but first of all, happy Halloween for everybody. That's, I think, on Saturday. But there will be a Halloween limited time engagement assignment for extra credit that will be released as a video form sometime between now and Halloween. And I did post a teaser for that already. If you've been following the Discord chat, it's on YouTube. It is the Singularity Engine assignment. And it's pretty cool. But it will be extra credit and there will be no PDF. It will be a video describing the assignment and an associated potentially skeleton file. I haven't decided yet. I might, if I do give you a skeleton file, it's going to be very basic and strictly using the Recursive library, since some of you may not be familiar with that. So yes, good morning indeed. But yes, that extra credit assignment is coming along, and it is based on the Star Wars parody by Aeronauts and Creepio in that. So that'll be pretty cool. So Lou like MB2 Lou? Wow. If so, then that's crazy. Oh my gosh. Such a long time no see. Good times. But if it was Lou, then you'd be in Poland, which is like 8 p.m. at night. So I don't know if it's the real Lou. Oh, it is you then, because you do have my postcard. Yes. It's just going to be assigned on Halloween, but it is not going to be due on Halloween. So yes, if you want to stay in for Halloween, then you can work on the assignment. If not, then you can work on it on a different day. So yes, but hello Lou. Long time no see. Lou is actually a real-time, full-time like developer, coder, you know. So yes, he's legit. He's from Poland. Poland, right? Yeah, you're from Poland, right? Yes, because I remember where I mailed the postcard was from Poland. So it just had to click for a bit, but yes. Okay. Well, this is class, so I shall go ahead and continue class. So anyways, today we are going to be learning about recursion again. And so last time, what we did was we did Fibonacci sequence in recursive code. And first we did it in iterative code, and then we did it in recursive code, but we haven't actually put it in the computer yet, technically, because we just did it in the iPad. So this is what we came up with for Fibonacci. However, we still gotta play around with this so that we can actually see the output being printed out correctly. So we're still working on that piece, okay? So in fact, I can already see we missed some curly brackets there so that we can close it like such. So, all right, peace out, Lou. I'll send you some messages, so we can play some game or something sometime. So, all right, but yeah, so basically, we're gonna go ahead and put this in code. So let's go ahead and do that. That's how we're gonna start. So let me go ahead and just make this a little smaller so that we can put it side by side here, and then shrink it a little bit like that. And so now we should be able to transition to this. There we go. Okay. So about that is good. Actually, I should probably move this to today's section. So there we go. Okay. So let's just go ahead and actually implement that. And I'm gonna go and do that in a new file just so that we don't run out of space. So we'll do it here. So this is a value returning function, by the way, and that is by design because what it actually returns is the nth Fibonacci sequence. And that's if we want to compute what the added sum of those numbers are, which basically we do because that's what gives us the next number in the Fibonacci sequence. So first of all, we have the base cases, right? There's two things to recursion. One of them is the base case and the other is the recursive case. There can be more than one base case. You can have as many base cases as you want actually, but typically you want to keep it to a small amount just because it involves a lot of coding for each of those base cases. So in the case of Fibonacci, that's going to be basically the two base numbers that you need because if each number to add that, you need to have the previous two. So in the very basic, you need to have two numbers as your base case. So in this case, that's return 1 and return 0. And then a recursive case is basically, you know, calling this function again, but with a smaller subset of the numbers. So in this case, we instead of passing the value of n, we're going to pass n minus 1. And we are going to add that to n minus 2. And this is a one-to-one match to what the formula from the, the math people would tell us for Fibonacci, which is this one here. So let me just switch to it. So this is the math formula that you would see on the book for Fibonacci, either this one or this one, probably this one. And so you can see here, there's 3 scenarios for Fibonacci, where n is greater than 1, where n is 1, and where n is 0. Now, this is counting from 0, but in math people, they might want to count from 1. So then that would be cases 1, 2, and 3, I suppose. So in that scenario here, you can see that for n is equal to 1 and n is equal to 0, we have a fixed value, right? So that's kind of like matching what our base case is doing. And then for n being greater than 1, we have this here. In fact, we could even code it in that exact format in the IDE if we flip the base cases around. So we say something like, if n is greater than 1, call this, otherwise, return, and then do like else if n is equal to 1, else return 0, basically. We could do it that way if we wanted to match it like that. However, I encourage you to always start out by listing your base case in the most obvious way. And so let me kind of give you what I'm saying with that. So one way to do this is how I coded it. And I think that's the best way to do it when you're getting started with recursion. But alternatively, what you can also do is you could rewrite this to say something like, if n is greater than 1, go ahead and do this. Otherwise, if n is equal to 1, go ahead and do that. And then here you can just either put an else like that, or you could just flat out get rid of this and just leave the return like that so that it falls there anyways. So either of these would work. However, as someone who's just starting to learn recursion, I would strongly encourage you to do it this way, because this is a little bit more direct into trying to explain what the base case is. Whereas here, you're seeing things in relation to when you're not calling the base case, because you see the recursion before the base case. And what I've been trying to insist upon you is that whenever you do recursion, you always need to check a base case before the recursive case, because if you go for the recursive case without a base case, you potentially could go on forever, infinite recursion, right? But here you're really still doing that. It's not as obvious because you have the if statement like this. So whereas here you're doing an if statement, and then immediately if that returns true, you go to the base case. Whereas here, if the if statement returns true, you go to the recursive case, but if it returns false. So really you're just flipping the logic. But again, this I feel is a lot easier to understand than this, especially when you get to something a little bit more complicated. So when you get to like actual algorithms of your recursion, then if you don't see that base case like this, then it just gets completely lost. And I'll try to show you some of those examples, maybe when we do like linked lists, okay? So anyways, but I do want to make you aware that yes, if you ever see like the recursive case first, you might be like, hey, there's no base case in this. Not quite, because it's probably wrapped around an if statement. Now, what you should never ever see is like just flat out a recursive call as the first line of the function. That just can't happen, because that probably means that like it's just gonna recurse forever, pretty much, because there's no checks to stop it, so it's just gonna keep calling that line over and over and over and over again. Yeah, so you would never see that. Okay, so anyways, so we got this here. Now this is not quite done yet because we forgot to put the return here, but this is going to compute us the nth Fibonacci number, but it's not going to print out the Fibonacci sequence. But let's see it anyways. So if we were to say something like Fibonacci 5, what we're going to get is what the, I suppose, 6th number would be, I think. This is recursion 2, so. Oh, well, it's printing it, but throwing it. It's computing it, but it's throwing it away. So let's go ahead and wrap that in a print statement so that we can see it. Okay, so we are getting 5. That does, oh no, that is correct, because here you can see the Fibonacci sequence from last time, actually. Oh, I forgot I did this LOL stuff. So we got 0, 1, 2, 3, 4, 5th index, 6th Fibonacci's number. So let's go ahead and maybe do an 8 there. So that should be 8 and then 13, so 22. 21. There we go. So as you can see, it's working, as in it's computing the nth number, but we're not printing it out. So while we could just do a for loop here to print it, let's actually do the printing as we go here. So first, let me tell you something that you might run into now. You're like, okay, well, let me just go ahead and see out, for example, a 1 here like that. And then do the same thing with a 0 here before we return it. And then for the recursive case, we need to maybe make a temporary variable first. I mean, technically we don't, but it's going to cause issues, so best to just do that. So we can do something like that, and then we can see out that with the space so it matches the other ones, and then we can return it. And so if we do this, we don't even need the see out anymore. In fact, the see out's gonna do something weird here. But you can see that we're getting all this massive amount of numbers. So you might be asking, like, why or what is happening here? And so let me get rid of the tablet, because you don't really see that anymore. So the reason for this is because of how technically inefficient this solution for computing the Fibonacci sequence is. Because here's the thing: when you're computing Fibonacci for this, and you're computing it like, let's say, the 3rd number, what it's doing is it's saying, okay, to get the 3rd number, we have to add the 2nd and 1st number together. So it actually makes 2 recursive calls, to the 2nd and the 1st. Both of those happen to return, 1 and 0, because those are the base cases, okay? But now let's look at one more scenario where we are returning the 4th Fibonacci sequence number, okay? When we're returning the 4th Fibonacci sequence number, what ends up happening is this. We start out by having Fibonacci 4, and that runs to the code, and n is equal to 4, so therefore it is not going to go into either the n is equal to 1 or n is equal to 0 base case. So it goes into the recursive case, right? And it makes 2 recursive calls with Fibonacci n minus 1 and n minus 2, which is going to be 3 and 2. Okay? So it needs to independently compute those recursive cases. And so once it computes them, then it can add the results together and get the final result back. But first we got to compute them. So it goes in and says, okay, let's go ahead and see what Fibonacci of 3 is. So it runs that code. So we are looking at Fibonacci of 3, which in this case n is equal to 3. So it doesn't go into either of the 2 base cases because 3 is not 1 or 0. And so it goes into the recursive case, which computes it on n-1, which is going to be Fibonacci 2, plus n-2, which is Fibonacci of 1. Okay? So then it runs into that by going left to right. So first it goes and does the 2. So when it's doing the 2, it's still not hitting that base case. So this is going to keep going one more time and making Fibonacci of 1 plus Fibonacci of 0. Okay? So let me line that up like that. So that is going to happen one more time. Okay? Finally, though, when we do hit Fibonacci 1, Fibonacci 1 is a base case. It just returns 1 or C outs 1. So this is going to basically C out a 1. And then it's also going to return it. So I'll just leave, return 1, C out 1 like that. Okay? And so it goes back to this function of Fibonacci 2, which now is going to add this to the result of Fibonacci 0. So it needs to call Fibonacci 0 to compute what that is. So it calls Fibonacci 0. And then in Fibonacci 0, we also have a base case, which returns 0. And C outs a 0. Okay? So now, because of this, we can see that the first output from their function is a 1 and a 0, which matches what you see up there. Okay? Even though we called it technically on Fibonacci 8, this is still going in that order. Okay, so now that we know what 1 plus 0 essentially is, Fibonacci 2 finishes. So Fibonacci finishes and returns a 2 and also C outs a 2. Technically in the other order, it first C outs and then returns, but it doesn't quite matter here. So I can still leave it like this. So now we know what this returns. So we go back to Fibonacci 3. Here's the issue. Fibonacci 3 is an addition of 2 and 1. So now it needs to go back and figure out what Fibonacci 1 is before it can add Fibonacci 2 plus Fibonacci 1 to compute Fibonacci 3. So you might think that, okay, well, we already computed what Fibonacci 1 is right here. So can't it just remember that? And the answer is, in the way this is coded with recursion, it does not remember that. It's that amnesia sort of scenario. So it's actually going to call Fibonacci 1 again, which fortunately is a base case, which is going to be like, okay, return 1 and then C out 1. But as you can see, we are already repeating ourselves. And also, after we see the 1 and the 0, when we get back to Fibonacci 2 and it returns that, returns a 2 out of that. Actually, sorry. 1 plus 0 is not 2. I don't know why I was thinking. 1 plus 0 is just 1, so that should be just 1. But yeah, so that actually prints out a 1. And then this Fibonacci 1 prints out a 1 as well. So that's why we see there 1, 0, 1, 1. Now we're going to go ahead and add 1 plus 1. Now that is going to be equal to 2. So this whole thing returns 2. So that's going to C out a 2. So that is why the next number you see there is a 2. Okay? From there, we just computed Fibonacci 3, so we're halfway done technically. Well, more than half, but Fibonacci 4 is the result of Fibonacci 3 plus Fibonacci 2. Fibonacci 3 we already computed, but now we got to go into Fibonacci 2 and compute that. So yet again, we know because we see that ourselves that it should be equal to 1 right there, because that's what it returned. But it's not going to be that easy because it doesn't remember that. So it's actually going to call Fibonacci 2, which is going to mean that it's going to have to call a function with Fibonacci 2, which is not going to go into either of the base cases. So it's going to go into the recursive case, and it's going to basically call Fibonacci 1 plus Fibonacci 0 again. So you're going to see the same sort of sub drawing here, which is called a tree. This is a tree. It's actually a binary tree, and you'll learn more about this in 302. But this little binary tree here is going to be rebuilt, which means it's going to be those recursive calls, which means that this R1 is going to see out a 1, and then this is going to return 0, and it's going to go see out a 0. So you're going to see here where's my output? Here we go. So we got a 2 there, and then this is going to see out a 1, a 0, and then whatever it returns, which is an addition of both of those, which is just a 1 again. And then finally, you're going to do 2 plus 1, which is 3. And all of that effort just to get a 3 back, which is, you know, I know it cut off the ending there, but it's 10121013, which matches exactly what we have there. So is the binary tree what you use for the Rickroll? Yes, in 302, yes. I was using that in 302. So in data structures, which is the next class that you take in the sort of sequence, well, you take 218 as well, but when you get to 302 with that sequence, you learn about data structures, which is different ways of storing data. One of those ways is, as you can see, a tree. And so there are different sort of components to that, such as how to build a tree, how to traverse a tree, which is basically how to print out a tree so that someone understands this is a tree. And in that example with the Rickroll, we had a traversal and we were trying to build the tree. And when we built it, we looked at it and it was actually a hidden message, which was never going to give you up. And of course, that was the Rickroll. So it's a very elaborate Rickroll, essentially. So yes, that's on YouTube if you guys are curious. But anyways, so this is your first introduction into trees now. And this is a recursive tree, and it's a very useful tool for you to be able to figure out ahead of time what the output of a recursive function is, right? So let's go ahead and kind of go full iPad here for a minute. So the way I did this is, of course, the way that the computer would do it. And as you can see, it's inefficient because we have multiple calls to the same functions. We have Fibonacci's 1 and 0. First of all, Fibonacci 0 is being called 2 times. And then Fibonacci 1 is being called 3 times. Because we also have here, I should have color coded them. Let me color code the Fibonacci 1s with this color. So here we have a Fibonacci 1, and here we have a Fibonacci 1. So we have 3 Fibonacci 1s being called. So the same function being called 3 times. Fibonacci 0 is being called 2 times, and so is Fibonacci 2. Fibonacci's 3 and 4 are only called 1 time each, which is a good thing. But as you can see, this is quite inefficient, and that's why you see that repetition of numbers in there. Okay? So I'm glad that we did this because you get to see that. And also because you will have to do one of these trees in the test. So that will happen. So you might as well start practicing them. And the reason why this is a binary tree is because there's 2 recursive calls in the function. In this case, you're adding the result of those together. But you don't necessarily have to add them together. You can just have the recursive calls there. So if there was 3 recursive calls there, so you see 3 function calls, then it would be a ternary tree, which means that it would have 3 lines coming out of each of the function calls, because each function is spawning 3 more functions essentially. So yeah, that's pretty much what that is. So do you guys have any questions on how this is working though? That's the most important thing, that you guys kind of understand the basics of how I made this recursion tree. By the way, there was 1 recursive call, so like a foo called foo and just foo itself 1 time each, such as if you're trying to recursively print an array, that would be sort of like linear. So it would not be binary. It would just be a line with a circle and then a line with a circle, a line with a circle, and so on. Kind of like what a linked list is, basically. So, okay, that's good. All right, and we'll do another example with this as well. But just to kind of show you just how repetitive this gets, and by repetitive I mean like inefficient, suppose that I said to compute Fibonacci 5. Well, Fibonacci 5 would actually be the addition of Fibonacci 4 and Fibonacci 3. So you'd do the same thing we did, but you'd also go ahead and do this entire subtree. It's not going to copy very well, but we'll try. You're going to have to do this entire subtree on this side again. So all those functions basically being redone. This whole side of the tree would be redone. So you'd have essentially 2, 4, 6, 7 extra function calls, right? So here's the thing though. when you're doing the test, you don't necessarily have to redo it. You can do exactly what I did there and like copy and paste. You know, if you're doing it in Paint, and if you're drawing it, then just, you know, redraw the tree, but you know what it should look like because you already did it, right? You're not a computer. You know that you already did Fibonacci 3 because you remember that. So I recommend that you do that in the test as well. So if you get something like Fibonacci 5, for example, and you do the left hand side first, which is all Fibonacci 4, and you're going to do the right hand side, just do exactly what I did here. Just make sure you actually copy and paste it without losing anything and having weird things like that afterwards. But yeah, so however, this does bring up a good question. Is there a way that we could make the computer also remember that it did something? It turns out that some programming languages have this, and it's what I was trying to remember the name last time. And I typically don't talk about this in 202. I talk about it in 302. Not sure as to the why, but I just remember that. So looking in my 302 notes, I have the link for a Python sort of concept related to this. Let me see if I have it here. I'll see if I can find it, and if I do, I'll post it on the YouTube video description. But I believe it's called neonization. It's like memorization but spelled differently. Memoization, something like that. There we go. Memoization and decorators. Yes, I think this is it, but that's not the same link that the one that I found. So I'm gonna go ahead and post this one since this is the one that I found. Oh, yeah, this works great. This is like talking about Fibonacci. So yeah, I'm sure this is exactly what it is. I mean, not the same one I found before, but pretty related. So if you go check that link out on your own time, it actually is talking about Fibonacci. Now, I haven't read it in detail, so this might be totally messed up. But I'm like 99% sure that they're probably going to be talking about what I'm saying. And essentially, what happens is this. Python remembers. It remembers. So when you do a function call on a certain number in this Fibonacci sequence, because this is not a function that is like modifying anything externally, it's sort of self-contained. And by that I'm saying is like if it acts as like a global variable and change it, that's a different story. But in this case, it's a very self-contained function. The only change is basically the parameters. And because those are being passed by value, that makes it even more self-contained than they were passed by reference. Because in that case, it actually would matter. So because of that, what Python does is it keeps a sort of a database. Well, database is bad. It's a bad name. No, forget database. It's a database. It keeps a table where it remembers what each function returned with each parameter. So like it remembers that Fibonacci 4 returned a 3. So the next time it sees Fibonacci 4, it will go ahead and actually return a 3 instead of calling it. And that will speed recursion insanely because you don't do all these repetitive calls. I don't know if cache, I mean, you could say cache, but like because I taught 219 over the summer, I've now had a hard associated cache with like actual L1, L2, and L3 cache and like hardware stuff. But yeah, you can say it caches the result. Yeah, that's a legitimate usage of the word cache. So yeah, so I'm pretty sure that that's what they're talking about in there. But if not, the term in Python is called memoization. I'm gonna post it on here so you can see how it's spelled. So that is how you spell it, and it looks like memorization, and probably it's a play on words on that probably because technically what's happening is Python is memorizing the results to this. So why would they do that? Well, let's go back to what we said last time. The big issue with recursion is twofolded. One of them is the fact that every time you do a recursive call, call stack, so it has to create memory to allocate to any local parameters in the function. The function itself takes a little bit of memory, and it takes time to set it up. Like, it's not something that, I don't know where, I think in 370 maybe you talk about it or something, but like, the basic idea is this. When you're creating a function, there is overhead involved to actually create that and to transfer the sequence from like main to the function or from a function to another function. That takes time in addition to resources. And it's way slower than just being in the loop that just goes back to the top of the loop. I mean, that still takes a little bit of time. That basically to move in assembly the next command from like the bottom of the loop to the top of the loop, and there's you know, pipelining and things like that sort of get broken when you do that, but then there's prediction to avoid that. So there's a lot of things involved to try to speed the computer as much as possible. But there's only so much you can do when it comes to a function, because it's an entire new thing that you're making with its own set of variables and scoping rules, etc., etc., etc. So it's slow and it takes space, which we saw very quickly can segmentation fault when you run out of memory if you're just calling functions recursively nonstop. Because of that, it's not very efficient to code. The other issue with recursion is this kind of stuff here, that you may be calling the same recursive function with the same parameters multiple times, such as is happening here with Fibonacci. So for this, Python solves this part of the problem with memoization, but also because it remembers what a function returns, it doesn't need to actually create that function. It also saves the other problem. So memoization kind of allows you to use recursion without the downsides of recursion. You can't always use it because, like I said again, this works because these recursive functions are just returning something, and they're very like self-contained. They don't affect outside variables. Other algorithms like quicksort, for example, is a recursive algorithm that you learn in Trio 2. It's a sorting algorithm, very fast. But the problem with it is that it's recursive, and each of the recursive calls modifies the array. So all the functions share the same array that you're sorting, essentially. So because of that, you can't use memoization for that one, because you can't skip ahead and do something before you finish this, and there's no value that you're computing. You're actually using the function to modify things. So this memoization only solves a certain subset of recursive scenarios. And again, loops are faster than recursion. They're better. But sometimes, for some algorithms, such as quicksort, it just makes more sense to make it recursive because it's more understandable, easier to code, actually. And like, for example, when you get to Trio 2 and do traversals for trees that we were talking about, the recursive version of that code is 5 lines of code. It's very simple. I showed them in the class. It's super, super simple. You do it iteratively, and it's at least twice the number of lines, and it just becomes a bit of a mess, to be honest. Like, you have to create a stack, which is the other thing I should talk about. Converting iterative code to recursive code and vice versa. So we'll do that in a second here. But yes, not to discourage you from recursion, but it's better to be real and tell you when it's good and when it's bad. Don't convert things to recursive just because it's cool. That's going to slow things down and bad things will happen. So anyways, but going back to this code, it does compute the next Fibonacci value in the sequence, but of course we get all these mess of things in here. So what we need to do for this to not happen is, that's a tricky one actually. How can we only print it out one time for each value? I don't even know for sure. We can start by commenting these out, but then we will never print out the 0 and the 1. Well, that might still work. We'll see. So let's try commenting these out and just leaving that C out there and see what happens. So we got rid of the 0s and 1s, but we still have the other ones that are recursive. So I don't think there's an easy way that we could actually do that without rewriting this function. I could, of course, call Fibonacci once for each value here in a loop, but if you wanted to do it recursively, how could we do this? We could do it if we had an array. So let's try that. But first, let's do that on a different one. So right now, this just computes a Fibonacci value, right? Okay, so if we created an array that we kept appending values to, then we could do it. This, of course, totally different than what because the math equation that we got for recursion was just trying to compute a number, right? What we're trying to do now is print out all numbers. So it's a different problem. So that's why it's not going to look like that equation. But essentially what we can do is we can say something like, let's just, actually, do we need, we don't need an array. We just need to keep track of the last two values. So we're going to call them previous one and previous two for first previous and second previous. And then n for the number of numbers, I suppose, that we want to print out for Fibonacci. Okay, so that'll be like, and we are gonna have to, for now at least, hard code that part like that. So let's say we want to print out the first 8 numbers. Okay, actually, I know how we can get away from not hard coding that. We can set these to be by default, the base cases like that, and then we can allow the person to do that. Albeit they could call this with bad values, but you know, it's okay. And then this does not need to be valid returning. Okay, so what I'm gonna do is I'm just going to basically add the two numbers together. Prev1 plus prev2 is going to give us the next number in the sequence, which is what we want to not just see out, but also to update values with. So I'm going to make it a temporary variable, so just make things easier. So we'll say temp2 is equal to the addition of the last two numbers. So that's the next number in the Fibonacci sequence. So we're going to immediately see out that. So we're going to go ahead and see out temp. We're still going to be missing the first two numbers of the sequence. We'll come back and fix that in a minute. I already have an idea on that. But once we do that, we're going to go ahead and decrease n minus 1 because we just printed one number. So we want to go back to 0. We also want to go ahead and avoid having infinite recursion. So our base case is going to be when n is equal to 0. Then we're just going to return without printing anything. Okay, and if we see that this is bad, then we can make it like equal to like -1 or something. We have to put nn to be the first parameter, so it's have to be a default. Yes, we do actually. Good call on that. Because default parameters have to go after required parameters. Otherwise, the compiler gets confused. So yes, good catch on that indeed. So yes, okay. So now all that we really need is the recursive case. So for the recursive case, we're going to pass a new n, which by the way, if we want to save a line of code, I suppose we could just do this and then just get rid of that. And then for the second parameters, we don't want to just pass the same things again like this, because then this is going to not go on forever, but it's not going to give us the right value. What we want to do is we want to update these. Previous one is not going to be what previous two is not going to be what previous one was originally. And then previous one is now going to be what temp is. So we're shifting it because like we have previous one and then we have previous two. So previous two, previous one is going to give us temp. Okay. So maybe iPad. So if we're trying to generate like, you know, 2, 3, 5, that's part of Fibonacci, right? So if we're trying to generate the 5, it's based on these. So this is considered to be previous 1 and then previous 2. So like first previous and second previous, okay? And so once we compute the 5, we're storing that in temp because that's the addition of previous 1 and previous 2. But then we want to update things. We want to make 5 be the new previous, and we want to make 3 be the new previous 2. Like that. So when I'm doing the function call, wherever I want previous 2 to be, which is the second parameter, I am now going to just pass previous 1, and wherever I want previous 1, I'm just going to pass temp. And that's how I came up with line 8, okay? It all seems very fancy, but we'll see if it really works in a minute here. Okay, and that's pretty much it. That is going to work, but I think it's going to print it backwards, but we'll see. Except, again, we still haven't done the base cases, but we can add like an if statement for that in a minute. Okay. Oh, I forgot to put the word end in here, and that will probably fix that error. Okay. So I guess let me put them with spaces instead of end lines. That's probably nicer like that. And again, we will also need to find a way to add an end line to this. But as you can see here, it's working for the most part, but we are missing the first value. We're missing the 0. We're actually missing the first two values, the 0, 1, because it's 0, 1, 1, 2. But other than that, it's working for the most part, okay? It actually is not printing backwards, which I thought it would, but that's great. So now, the way we can sort of fix the base case is we can just put it in before the return statement here. We can either cheat and put them both together like that, or if we see, well, let's understand what we want. Do we want fib0 to print out a 0 or to print nothing? Do we want fib1 to print out 0, 1 or to just print 0? Depends on how we were trying to do that. We can do, I don't know if you guys have a preference, but what I'm going to do is I'm going to say fib0 is going to print out the first item, which is just a 0. Fib1 is going to print out 0, 1, and fib2 is going to print out 0, 1, 1. So let's go with that system. So let's just test this like this for now. Okay, so that breaks that. Okay, so that cannot go there. If n is equal to 0, so we want to print it out first. Okay, so we're gonna say if oof, that's a tricky one. How do we print it out the first time we only do it? We could do it with a static variable, but that's not too elegant. I was thinking the same thing. You know, how could we do this? We need to know the first time that we called a recursive function. I know we can do it with a static, but I'm trying to see if there's a way we can do it without the static. Well, okay, if we add another, okay, there's two things we can do. Option 1 is we can add a static. Option 2 that I can think of is we can add an extra parameter that keeps track of what the max value is. So we could say like, you know, like int max, which is normally equal to n. Can we do that like that? Does that code compile? Well, if we have a comma there. Well, it won't compile. This won't compile, but I just want to see if the function parameter will compile. Local variable may not appear in this context. Yeah, so it will not compile with that. Okay. So one way is we could do something like that and then just make it a required parameter like that. And then just pass in max without modification. One way would be to do that, but it's not pretty because I don't like the fact that I have to now pass in 2 parameters. So let's use a static for that one. So how to use a static with this? Okay, so remember how static variables work with functions. So there's only one instance, no matter how many functions you have or function calls that generate functions of their own, especially with recursion, you only have one copy of the variable, and that is shared between all of them, one instance of it. And so that is useful because then you can sort of communicate between recursive functions. So if I go ahead and create my static, and call it max, I can initialize that. Oh, can I initialize that to n? I think I should be able to the first time it gets called, but I'm not sure actually. Let me see if that is going to compile too. Too many. Oh, hold on. I gotta get rid of. Wait. Oh, here. That. Let's see if that. I'm not even sure if that will really compile. Okay, that compiled. Okay. Ooh. All right. So the first time that the function gets called, the static gets generated and it gets populated with n. The problem with this is that it's only going to work one time and then it's going to break. So that will be the disadvantage, I suppose. to oh no, because when we do the base case, we might be able to reset it, but nope, I don't. I think, yeah, this is like a one-off that we'll have for this. So that's not the best of solutions. Because this will work. Okay, well, let me show you how this works, and I'll show you why it breaks after the first try. Yeah, okay, so if we do the static max, then we can say if max is equal to n, then we can go ahead and see out 0, 1. So that worked out 0, 1, 2. We have one too many things for that. We can say if n is less than or equal to 1. Okay, so 0, 1, 2. So now the 2 matches the index of the number to print. So let's test this with a bigger number now. Like that. 0, 1, 1, 2, 3, 5, 8. So this works out great. And then 0, 1, 2, 3, 4, 5, 6. However, the problem with this solution is that if I call this again with the static is still set to max. So actually, if I call it with 6, it's still going to work, funnily enough. But and by the way, I can take advantage of this return to put an end line here, and that's actually going to be useful for me because that for sure will be called at the end. So, hold on. Okay, there we go. So that works out. However, if I change this to like a 4, it's already breaking. You see that? It does not print out the 0, 1s. So the static solution worked out in this case only one time, and then it breaks after that. If prep is equal to 0, see out 0, and if n is greater than 0, also see out 0. Ooh, that's a good idea. That might work actually. No, oh no, it's not gonna work because it's gonna. The problem with that is that prep 1 and prep 0. Aha, I have another idea for that actually. Yes. Ooh, yes, this is gonna work. I have an idea. Okay, so here's the reason why yours doesn't work though. So yours doesn't work because we want to print out 0. Oh wait, no, it actually would work, I think, because no, actually, what you're setting it might work. Yes, it will. I think it'll work too. Yes. Okay, so let's try that. So you saw the static one works, but it doesn't work for more than one call. So it's kind of like a patch, but doesn't really patch things. So I think what you're saying will probably work. Yes. That's a good idea. That's brilliant, actually. I love that. Yeah, it worked. Well done. I shall give you 100 points extra credit for that. So send me a DM after the lecture, or send me a message on Canvas, because that is very smart. I am impressed with that. That is cool. That is cool. That is cool. That's right. That's pretty cool right there. I didn't think about that, so I'm proud of you for that. So yes, you definitely deserve some points for that. Okay, so I'm not gonna touch that anymore, but I am gonna make a second version of this that I wanted to show you how we can. Let's say we want to print it backwards. Okay, so if we wanted to print it backwards, what can we do to this code to make it print backwards? Well, what we could do is we can. I don't know if I actually want to even do that. We could move the recursive call before the temp. Let's see what happens if we do that. Of course, this is going to get messed up, but other than that, let's see if it works. Fib was not according to scope. Oh, I called it Fib 2, not Fib 1. Fib 2, let's call it with 6 and see what happens. That almost works, except for the first two values, but that's okay, because now we can just throw that in here, in the base case. Why did it print out of order? That is weird. Oh, I see why. Okay, so maybe we flip this logic around. We want to put this after this here. I'll show you what I'm doing. I just want to do it first, because I'm not sure if it'll work. But if we flip this now to say if n is less than or equal to 0, then if n is greater than 1, I think. Greater than 1 or greater than 2. It's one of those. Let's just try greater than 1. If it breaks, we'll do greater than 2. Okay, come on. Okay. Okay, so then we have to make it greater than 2. Why? Why doesn't that work? When it gets to 0, oh, it's still doing that, so that's why. Okay, so in that case, we can put it in here. If n minus minus, if that is now less than 2, maybe we can put that in there. Okay, we broke it terribly. Let me make sure that that's still somewhat working. Okay, so we gotta figure out a way to append the 1 and the 0 after the last call. So the last call of this is when n is less than 2. So I suppose if n is equal to 1. If n is less than or equal to 1. I think that's what we want to put in here. And if we do that, then this should work. It didn't work. N was greater than 2. If it's equal to 2, it's not going to work. Okay, so maybe less than or equal to 2 here. Okay, let's try that again. That's not working. Okay, so we were able to flip it backwards. Let me talk about what I've done so far, even though this part is not working. So this was printing it forwards, but notice the little trick I did. Remember with this whole head and tail recursion, I moved the C out on top, or I moved the C out from being on top before the recursive code to being beneath it, as you can see here. Doing that basically flips the entire list backwards, with the exception of the base case, which yet again is proving to give us pain. So interestingly enough, we just need to figure out how to fix that part. As to why I can't get it fixed, that's what I'm trying to think here. I think maybe if we make this, what if we flip this to a 1? 5, 3, 2, 1. So we get the 8 up here now. So that's definitely not the answer. If n was greater than 2, it would be 3. And then it would become 2 here. So if n is equal to 2, let's try that. 3, 2, 1, and then it doesn't go in. If n is greater than 2, 3, 2. If it goes to 1, it would not go in there. It would just return. Not sure how to do this one. The inner if should be n is less than or equal to 2. I can try that. I think I might have tried that. I don't even know if I tried that one already. Nope, that does not work. Yeah, it has to be at least 2, but we're not thinking of some scenario. Four, 3, 2, 1. We just need to find the case. How about where n is equal to okay, so just if I was to put this as a 6, would this work? We get a 2 and a 3 now. So oh no, we don't get anything printed out. Okay, and if this was 5, I think if it was a 5, it would work in this specific case. Yeah. Okay. So okay. So now I see what is happening. So this will work for this specific number, but we hard coded that. So basically, the last recursive call, when we do fib6, when fib5 is coming back from here, and we're doing fib6 here, we see out the last number, n is equal to 5. So that's when we want to print it. So really, we want to print it again when n was the original value. Okay? So we need to have a max again, which again, we would need to have an extra parameter for to remember that it's the max. So I don't really see a way around that easily. But again, if we did set it int max gets n, and then we said n is equal to max minus 1, I guess. Max minus 1. Then this will work, but yet again, if we call it again, then a different value, then it's going to break because of the static issue. So if we do like 7, then as you can see, it just died completely. You get like a random thing printed out there. So it does not work, but it works if we do it only one time. So it's okay. But anyways, that's more complicated than you would want to do anyways. So what you could also do is you could make this function store something into array and then just print that array backwards. You could do that. Or you could use a stack once we talk about stacks. But anyways, these are some examples of recursion. And hopefully that's kind of starting to kind of get you warmed up to recursion. Let's see if there's anything more that I want to say. I have other examples of recursion that we can play around with, and we will. But for the last example today, let's do something basic like printing an array. Okay? So I'm going to get rid of this one because it's just kind of a bit of a mess. So, blah. I don't want to confuse you guys if you try this later. But hey, explore this and see if you can figure it out and post on Discord. So, yeah. But, so basically print out Fibonacci sequence backwards. That's sort of the mini challenge, I suppose. Okay, so for now, let's just say we want to print like an array backwards. So let's say you make a vector. Actually, let's just make an int array, because then I can use that one syntax to initialize it quickly, right? I'm sure you guys have seen this syntax before. I believe it works. make sure before I even say it works, and it doesn't work. Yeah, it works. I forgot what the name of this is, but you're basically initializing a constant array. So this is basically hard-coded, so it's constant. But yeah, so anyways, say we wanted to print that array backwards and forwards recursively for both cases. Okay, so we're going to call it recursive print forward, and we're going to pass in the array and the size, and then we want to print backwards. I don't know how do you abbreviate backwards? Like backwards. I don't know, whatever. We'll just say it like that. I think that's it. BKW. Okay, so let us go ahead and implement one of those, and then we'll do the other one. It'll be quite easy to switch them, as you'll see when we just flip around the location of the recursive call. So this is an int array. And then we have the size parameter as well. Okay, I'm so used to like pointers that I kind of just want to do that instead of that, and see if it just lets me do that. And then we also have the other function, which is the backwards. And then let's just make sure that that works. This is now. Okay, all right, so now we want to print out the array. So we're going to do it recursively. If it was iteratively, we would just use a for loop. But in this case, what we want to do is we want to split the problem into a smaller piece every time that we do the recursion. You can think of the recursion like a person with a pickaxe mining. You know, it's mining a wall, and every time he hits it, he gets closer to finding the gold. So essentially, you want to say pickaxe once and then do everything again, which is pickaxe again. So the pickaxe part is going to be, of course, printing out one of the values. So in this case, we are going to print out size. But size is, of course, out of bounds, so we're going to do size minus 1. Okay? The next thing we're going to do is basically get closer to our goal, which is essentially to call this function again, but this time to call it with the size change because we're slightly closer. So in that case, it would be, again, size minus 1. Okay? Although, technically speaking, that is going to print it backwards. So, yes, let's actually put that in the backwards one. Okay? So, before we do the forwards, I suppose, let us see if this works. So we get a 5. Actually, this should just go forever. What have I done? Oh, I see. I have backwards instead of forwards here, which I'm glad, because otherwise this would have recursed forever, and I wanted to show you that. So here. So as you can see, it printed more than just or 5 numbers, right? And that is because I gave it away already, but we have no base case. So we need to add in the base case. So what can our base case be? Well, if we're printing down, we can say if size is equal to, I suppose, 0 minus 1, which would be -1, right? Or it's technically less than or equal to that. Just, I feel safer doing that kind of thing. Why -1? Because we're doing this whole hack with the size minus 1 here. So when size gets to, actually, sorry, if size is 1, then we want to stop. So if size is less than 1, because then 1 minus 1 will be 0, so we will never go into a negative value. So the last value we want to print out is for 0. So size, if size was 1, it would still be okay. So if size is less than or equal, so I suppose we can flip this to greater than, actually. We can say if size is greater than or equal to 1. Yes, that will work like this, actually. However, I'm going to show you how to do it in another way in a second here. So here we go, 5, 4, 3, 2, 1. However, if you want to do it the way where you actually show the base case explicitly, then you can do that very easily by, actually here, I'll leave this version and then I'll add the other version. So if you want to be explicit about the base case, then you can say if size is less than 1, then just return. So that's your base case. And then if you are not in the base case, then you're just printing and calling recursively. Okay, so if size is 1, then it will not go in there. So I think this should be okay. Hold on, let me call this 2. And then call this twice. Okay. So as you can see, we get 5, 4, 3, 2, 1, 5, 4, 3, 2, 1. If we add an end line, we'd get them in different lines, but we'd actually add the end line in the recursive case because we know that's going to run at the end, right? So we can just say cout end line. And then for this one, I guess we can add an else. Cout end line. And there you go. Okay. So last thing, I know we were out of time, so we'll do it really fast. How do we print it forwards? For the forwards, there's a lot of ways, but the easiest way is just to get an extra parameter in here that we call max. So just like beginning and end where you want to print. So 0 to 5. As long as we do that, then this is just a piece of cake, because then we can say int start and int size. And then we can say cout a start and then call the function by increasing it. So a start plus 1 size, and then our base case being if start is greater than or equal to size. Technically equal to is fine, but again, I like to be safe about that. I don't know why. It just makes me feel safer if I somehow miss that one spot. Let me see. If start is greater than or equal to size, return cout start a start size. But that's all fine, so we just need a comma. Let's get rid of that. That's kind of annoying. Okay. Oh. Okay, there we go. We're missing a curly bracket at line 20. Yeah, we had some issues, glitches. But anyways, you can see there that it worked out. I just have to add one more thing and we'll be fully done. See, the lecture just wants to end. That's why I just immediately like kicked to that. Okay. Like that. Okay, so as you can see, we don't have an end line yet. I don't know why I didn't get that end line. Maybe I didn't save it. Start is greater, return. Oh! Because I gotta put the return after the cout, not, otherwise it will never get called. There we go. So 1, 2, 3, 4, 5, and then 5, 4, 3, 2, 1. So very briefly, how I did this is I essentially went ahead and have a starting index and an ending index, and every time I call the function, I increase that starting index so it prints the next number available, right? Very cool thing about this version of this code is that if I go ahead and flip this and put it down here, it is yet another way to print backwards, actually. See that? Now it's printing backwards again. We lost the end line thing, but it's printing backwards. So that's pretty cool. We'll leave it like that though, as we had it before. But yet another way to print backwards. So as you can see, depending on what your recursive call is in relation to the print statement, just like we were doing with Fibonacci, you cannot make it print backwards. So anyways, really we're just trying to practice a lot of recursion, and that's probably what we'll do next time too. Just so that'll be like the last day of recursion practice. Next time what I'm going to focus on though is, while you can't do this for every single scenario, there's a lot of scenarios where there's a very simple sort of algorithm that allows you to convert recursive code into iterative code and vice versa. So that's something that we're going to explore next time. And then maybe just find more problems, maybe more complicated problems that we can kind of work through and do recursively. But yeah, so your next assignment, I think it's supposed to be the recursive one, or exception handling. I'm not sure. If it's exception handling and there's something that I need to emphasize on, then I'll also throw that in the next class. But yeah, that's pretty much it. So like I said, for now, keep your eyes posted for the Halloween extra credit that will come out pretty soon. But other than that, that's the lecture. So just a bunch of recursive practice today. So thanks for watching, guys. Am I going to post it? I will post a Canvas announcement along with a page like you normally get. But instead of a PDF, it'll be just a video. It might have some writing in the page, but mostly it'll be just a video. In fact, I can show you. I can run the code. Yeah, it's working. So I'm actually running this in Windows, but yeah, this thing is actually like moving. And if I move it faster, it moves faster. I don't know how this looks on the stream, but I forgot the letters already. I think it's, which letter is it? A. Yeah, so A is the singularity. And if any of the asterisks collide with the singularities, then they're sort of triggered. And then if those triggered ones make contact with any of the other untriggered ones, then they trigger them too. And soon enough, everyone's triggered. So that's pretty much it. Sort of shows you, it's also a good simulation of like an infectious disease. So like there's a single patient 0 did not create a pandemic, but if we do it again, patient 0 did not create a pandemic. Third time around, did not. It only survives for 10 moves before it disappears. So it doesn't always contact anybody. But now, oh, there we go. It contacted one person and that contacted 2. And soon enough, if we speed it up, it spreads it out to everybody. So it creates that singularity. So that's pretty cool. It's like a little thing. I'm pressing a button to advance it one step in time. And then I have Q to quit. So, and then these parameters indicate how big of the game board I can do. So I can make it bigger or smaller. If I want to see the usage of it, I can do this. So I'll explain this all in the video, and I'll put some skeleton code. So I have the odds for, because if, oh, that's the other thing. If one trigger comes in contact with a not triggered one, it doesn't automatically trigger it. There's a percentage. So I have it at 50%, so 50-50 chance. So if you want to have a higher rate of contagion potentially, then you can raise that higher. So actually, oh no, that's a fraction value. So I guess if you increase that, it'll make it lower. So you want to put a fraction there to make it higher, I think. I don't know. I'll mess with that. But yeah, it's pretty cool. So anyways, that is going to be a potential Halloween assignment, unless you want to do it after Halloween, I suppose. All right. So, yep. Okay, then. Well, if not, then have a good Halloween. Have a good weekend as well. And I'll see you guys next week. Stay safe and peace.